Hello and welcome to the screencast on physical and chemical properties. This is lesson 1.04 in your electronic textbook and workbook. I'm Mrs. Willie and let's get started. Let's discuss properties. Properties are characteristics of pure substances. Remember, last lesson was how to determine whether a substance is a mixture or a pure substance. So we're going to be focusing on pure substances that are made up of the same particle. So when we're speaking about that, we're speaking about substances that are all of the same particle throughout. So the properties of matter fit into two categories: physical properties and chemical properties. Physical properties are observed without changing the chemical bonds within those particles. Chemical properties are observed when a substance interacts with another substance, or when a chemical bond breaks and or forms, or both. So let's start with physical properties. Physical properties are observed without changing the chemical bonds, so they can be split into two subcategories: intensive and extensive. Intensive physical properties do not depend on the amount of matter present. So an example of this is if I have 1 cube of ice, or if I have an entire glass filled with ice cubes, the properties that we discuss in the intensive subcategory do not change. They do not depend on the amount of that matter present. They can be used to identify a substance, and then most physical properties can be classified as intensive, as you will see some examples we talk about here coming up. Extensive physical properties depend on how much matter is present. So if I'm going back to the ice cube example, extensive properties would be properties describing both of these, and notice they would have to change. So if I'm talking about the 1 ice cube or the glass of ice cube, the properties that are in this column, extensive column, change. Any property whose value changes with changes in mass, volume, length, or the number of particles. So some examples of intensive properties could be color, odor, texture, melting, boiling, and freezing point, state of matter, so solid, liquid, and gas, like we discussed in our last lesson, luster, or the shine of an object, malleability. The definition of malleability is the ability to be beaten into sheets. So this is pertaining to metals, pure substances, or alloys. That mixture of metals, they have a malleability associated with them. Ductility is the ability to be drawn into wire. This is also mostly talking about metal substances. Conductivity, the ability of a substance to permit the flow of thermal energy. We will talk about some more examples of intensive properties in the next slide. So this conductivity example is very much like these other examples, and we're going to give you some helpful hints to determine whether a property is intensive or extensive. So on this next slide, you can see you have density, you have temperature, pH, specific heat, molar mass, and molar concentration. And it's okay if you don't know what all of these terms are. We're going to learn them throughout the year. But there is something that you can notice that is in common with some of these terms, just like there was on the last slide. If you notice, the units in these terms are in ratios. So if you see the top, and take a note up here, a property that is defined by a ratio where two or more quantities, so speaking specifically of extensive properties, are being compared is intensive, since these ratios do not change no matter how much matter is present. So going back to our ice cube example, the density of 1 cube of ice is the same as the density of the ice cubes inside of our cup. It does not matter how much matter is present, the mass is present. The density of water at this temperature and pressure will always be the same because it is in the solid form. The same thing happens with molar concentration, molar mass, specific heat. Specific gravity I skipped over, which is the density of a pure substance compared to density of water. So key word there is density and density. So again, I will have a ratio. So making that an intensive property. Extensive properties, remember, do depend on the amount of matter present. Those are mass, weight, volume, length, number of moles. It's okay that you don't know what a mole is. We're going to learn that later on. But for now, we are just trying to introduce the vocabulary word to you. So the unit for mass is grams. The unit for weight is pounds. The unit for volume is liters. The unit for length is meters. And then the unit for number of moles is MOL, which means the number of particles, that's speaking of atoms, ions, formula units, or molecules in a sample. All of these properties depend upon how much matter is present and can quantify that amount of matter. So an example of comparing properties. So you have the intensive property of appearance, melting point, molar mass, and magnetism. And I'm going to compare that. So I have an iron sample. I'm combining it with an oxygen sample, and I am producing iron oxide. So the top of this is actually an example of a chemical property, which we're going to talk about next. And this is just a visual. This is not a balanced chemical equation, but just showing you how you can break the bonds and then form new bonds. That would be a chemical change, and it would have chemical properties associated with it. But you can look at the physical properties of each of these reactants and the product to determine that a chemical change has occurred. So chemical properties are when compounds are broken apart or combine to create a new product. Molecule chemical bonds break into individual atoms, and formula units break into ions. Remember, ions have charges. Atoms are neutral. The individual atoms interact with each other or with the individual ions, and then the individual ions interact with each other or the individual atoms to form new bonds, and a chemical reaction occurs. So in our example here at the bottom, I have a compound, a diatomic element that creates a new compound and another new compound. So I know that bonds were broken and new bonds were formed. So some chemical properties are the ability to react or to not react, the ability to oxidize or corrode. Remember, corrode, we learned about that in our safety lesson. It damages the tissues and the skin on your body. Some examples of this would be tarnish, rust, decomposition, or you're seeing if it does not do that. So it's the absence of or the presence of oxidation and corrosion. The ability to burn is combustion and or flammability or not. So those observations are all chemical properties. So now let's discuss changes. Changes are the acts of making or becoming something different, and we're going to talk about those into two different subcategories in chemistry. You can have a physical change, which is a change that does not involve the change of the identity of the substance. So chemical bonds are not breaking and reforming. In a chemical change, one or more of the substances is converted into one or more different substances. In other words, chemical bonds break and then form, or both. So, in order to determine whether a chemical change is happening, We use the acronym to help us remember. City geologists love their silent phones. The C represents color change. This has to be an unexpected color change. So if I put food coloring into water, I expect that color change to happen. That would not be an example of a color change. Whereas an example of a color change unexpectedly happening is when you're sitting outside in the summer and you see lightning bugs outside and there's that glow of light. Geologists represent the G, which is gas production. I can see bubble formation here, or I smell an odor. Love stands for L, light production. Again, unexpected light production. There stands for the T, temperature change, unexpected temperature change. If I boil water, I expect it to get warmer. If I put it into the freezer, I expect it to get cooler. This would be an unexpected or exothermic or endothermic reaction. Silent, the S stands for smell production, unexpected. This relates to gas production. Phones, the P in phones is precipitate formation. And no, we are not talking about the rain that comes down from the sky. We are talking about when a solid is formed from two aqueous solutions. That is what a precipitate is. So again, city geologists love their silent phones. If you observe any of these occurring, you can say that a chemical change has occurred. Physical changes are all the states of matter changing. So if I'm thinking about a phase change, when I go from a solid to a liquid and melting occurs, when I go from a liquid to a gas, and let me fix that. I meant to underline vaporization. Because when I go from a liquid to a gas, vaporization occurs. And when I go from a gas to a solid, this is called deposition. My favorite example of deposition is snow. Snow goes straight from the gas phase to the solid phase. And then it also works going the opposite direction. If I go from a solid to a gas, that is sublimation. An example of sublimation would be dry ice. If you've ever experienced a Halloween party where there is smoke and quotation marks coming outside of the pumpkin's mouth, that would be an example of sublimation. Condensation is when a gas changes into a liquid. You can feel this a lot here down in the south when you leave an ice glass of water out and the condensation forms on the outside of your glass. And then when you go from a liquid to a solid, this is freezing. You do not need to worry about the phase changes going from a gas to a plasma. They are here, so if I go from a gas to a plasma, that would be ionization, and if I go from plasma to gas, that is called recombination. But this is beyond the scope of this course, and we will not be covering that in our course. So the enthalpy of the system refers to the sum of the system's internal energy and the product of its pressure and volume. As you travel up this diagram from solid phase to plasma phase, the enthalpy or the internal energy is increasing. So phase changes can also be written where you have your state signifiers that you learned in your last lesson. So in this example, the solid water is changing phase to liquid water. So pay really close attention when you're looking at these chemical equations on whether or not the state of matter qualifier changed. So again, you have solid, liquid, and gas. Notice in all of these examples, we're talking about a pure substance, not a mixture. All of these would be water. So absorption of energy, the temperature increases, so the kinetic energy is increasing as I'm moving through the solid phase, so the kinetic energy is increasing. Then I go through the phase change of melting, and kinetic energy remains constant, and the potential energy increases. The potential energy is that stored energy in between the particles. So notice the distance between the solid particles and the distance between the liquid particles increases, so the energy that is able to be stored in those distances is increased. That is why the potential energy is increasing as you go through the phase change. Then, as I'm going along through the liquid phase, the kinetic energy is increasing. Then I go through another phase change, kinetic energy remains the same, and potential energy increases. And the same goes here. The distance between the particles is larger, but the potential energy while in the gaseous phase remains the same, and the kinetic energy is increasing. That brings us to phase diagrams. So another way to view what is happening with the physical change and is a phase diagram. A phase diagram is an illustration that combines pressure and temperature that will result in that pure substance going from a solid, a liquid, or a gas. So pressure, in this case, is the force on the object. This force is coming from the environment, and it is on the pure substance or around the pure substance. Some things that you need to know about a phase diagram is that all of the lines are a phase change. All of the lines are a phase change. So if I cross the line, I am changing phases. The solid is always on the far left of the phase diagram. The gas is always on the bottom and to the right, and the liquid phase is always in the middle top portion. So if I'm going from the solid, there's a temperature change, and the conditions that they give me are moving from a solid to a gas, then I would be going through sublimation if I cross this line. And then if the temperature change is starting in the gas and then goes to the solid, then I'm going through decomposition. Because as we talked about in the last slide, temperature is a measure of kinetic energy. So the kinetic energy is either increasing or decreasing, but remaining the same as I cross that line and while I go through the phase change itself. Same thing happens between solids and liquids. I am going through melting as I go from a solid to a liquid, and I am going through freezing as I go from a liquid to a solid. Condensation as I go from a gas to a liquid, and vaporization as I go from a liquid to a gas. At the ends of these lines and all throughout while you're touching the line, the phase changes, not the phase changes, but the phases are in equilibrium. So while I am on this line, the liquid and the gas phases are in equilibrium. While I am on this line, the solid and the gas phases are in equilibrium. While I am on this line, the solid and the liquid phases are in equilibrium. Where the three lines meet is called the triple point. This is a specific pressure and temperature where all three phases, solid, liquid, and gases, exist in equilibrium at the same time. The critical point is the pressure and temperature at which both the liquid and the vapor phases are indistinguishable. The critical point is right here at the top of that line. Thank you so much for listening to my screencast today. I hope you enjoyed it, and see you next time.